Hello. So we're moving on to actually dealing with quantities. And this is something we've sort of talked about already. Basically, we're going to be talking a lot about the mole. And so we've already sort of discussed it a little bit, but now we're sort of going to get into the sort of calculations that we're going to be doing when we're dealing with moles. And then basically this means doing grams to mole conversions, figuring out if you have a certain quantity of reactant, how much product are you going to get, the concept of limiting reactants and excess reactants, and balancing equations, all that kind of stuff we'll be talking about today. Okay, so we're going to define the mole. I think you pretty much know what that is already. Um, but we're going to learn to use it doing balanced chemical reactions. And we really haven't done a whole lot about balancing chemical reactions because this is probably, again, one of the most important things we're going to be dealing with. So we need to be able to take figuring out if a reaction like hydrogen gas plus oxygen gas gives you water, exactly what are the ratios of hydrogen to oxygen. And we know that those ratios are not in terms of grams. Those ratios are in terms of moles. So we're going to need to convert mass to moles and then back again in order to figure out exactly the mass of products and reactants in an equation. Okay. So we use the term mole to represent a lot of atoms or molecules. And I've sort of told you that I'm not a big believer in memorizing Avogadro's number because we don't measure the number of atoms. And generally, we don't really care what the number of atoms are because we can't count them. What we really need to know and what we do care about is measuring the mass of atoms and the mass of a reactant or a product. And the mass of reactant and products is determined by the number of moles. And so a mole, as I've sort of mentioned before, is just a unit. It's a chemical unit. It's a chemical reaction equivalent. So 1 mole of one type of atom reacts with 2 moles of another type of atom and creates 1 mole of a molecule. That is something that we can see and determine. So the mole determines how reactions take place, and the grams determine how we can measure those. So 12 grams of carbon-12, that is precisely 1 mole. That is, in fact, the definition. That tells us the number of atoms, and the number of atoms is Avogadro's number. So I'm not going to be giving you questions determining the number of atoms, or the number of molecules, or something. What I will be doing is ask you to take grams of something and then convert them to moles. Because, like as I said, moles is something we're going to be working on over and over and over and over again. So these are the molecular relationships involving moles. So if I have 1 molecule of this, it's got 2 atoms of carbon, it's got 6 atoms of hydrogen, and has 1 atom of oxygen. If I have a mole of that, that means I have 2 moles of carbon, 6 moles of hydrogen, 1 mole of oxygen. And that's how I determine the molar mass of this particular molecule. Because I can use my good old-fashioned periodic table, which everyone has printed out in front of them at all times. I know how much a mole of carbon weighs. I know what the mass of that is. I know what the mass of hydrogen is. I know what the mass of oxygen is because it's right there in the periodic table. We know that the mole, 1 mole of carbon, for instance, weighs 2.011 grams. Because even though it's mostly carbon-12, almost all carbon is carbon-12 isotope. There's some carbon-13, there's some carbon-14. So a mole of carbon is going to contain a little bit of 13 and a little bit of 14. And so a mole of carbon doesn't weigh exactly 12 grams. It's a little bit heavier. Same with hydrogen. Most hydrogen is protium, right? 1 proton. So it weighs 1. But we also know there's a little bit of deuterium, there's a little bit of tritium. And so instead of a mole of hydrogen weighing exactly 1 gram, it has the mass 1.008 grams. So all we need to do is just put those masses together, figure out how many moles of these atoms are present, and calculate the molar mass of our molecule. The other thing we need to remember is that these are strict ratios. There is exactly 2 moles of carbon in 1 mole of that molecule. There are exactly 6 moles of hydrogen in this molecule and exactly 1 mole of oxygen. So these are the ratios. So if I'm given in my reaction a certain number of moles of oxygen, I can automatically compute how many moles of the product I'm going to get. If there's 1 mole of oxygen atoms, there's going to be 1 mole of product. If I know how many moles of hydrogen there are, I know exactly there's going to be 1/6 as many moles of product, because there's 6 moles of hydrogen in 1 mole of the product. So I can always remember, when we're doing conversions, we're converting mass to moles, or we're converting moles to mass, or we're converting centimeters cubed to liters, and we're doing all these conversions. This is yet another conversion we're going to be using, converting mole of reactant to mole of product, or vice versa. So we have to remember that these relationships are given in the formula for the particular molecule. Okay? So here's an example. So if a sample consists of 2.5 moles of ethanol, and so the molecule we were talking about before is ethanol, how many moles of carbon atoms, hydrogen atoms, and oxygen atoms does it have? Well, we're just going to do a conversion like we have been doing. So we start with 2.5 moles of ethanol, and then we multiply that by our conversion factor. So if I want to figure out how many moles of hydrogen atoms, for instance, what's the ratio of hydrogen atoms to ethanol molecules? Well, I look in the formula. There is 6 moles of hydrogen for every 1 mole of ethanol. Then, as we've always done, we clear out or eliminate the same unit that's on the top and the bottom. I have moles of ethanol here, I have moles of ethanol here, and the only unit I have left is moles of hydrogen. So 2.5 times 6, so 12, 18, nope, 15. 2.5 times 6, so that gives me 15 moles of hydrogen. Now, one thing to remember, and that's going to be an issue and a really common mistake that students are going to make, is that you're going to say, well, hydrogen doesn't exist as H, it exists as H2, right? We know that. We know that hydrogen doesn't exist as an atom. It exists as a molecule. That's the most stable form of hydrogen. We don't have 15 moles of hydrogen molecules. We have 15 moles of hydrogen atoms. So if we want to go back to hydrogen molecules, then we need to do another conversion and say if we have 15 moles of hydrogen atoms, how many moles of hydrogen molecules would that be? And since there's 2 atoms in a molecule, that would be 7.5 moles of hydrogen. Okay, so same thing would be true for carbon. Instead of 6 moles of hydrogen, we would have 2 moles of carbon atoms. And so our answer would be 5 moles of carbon atoms. And since there's a 1-to-1 ratio of oxygen to ethanol, if there's 2.5 moles of ethanol, there's 2.5 moles of oxygen as well. Okay. So 1 mole of a substance has the same mass in grams, and we've been talking about this for quite a while, that 1 atom has in our old friend atomic mass units. So all of the numbers given in the periodic table are for atomic mass units. But the thing that makes that easy for us to do the conversion is that it's exactly the same mass as 1 mole in grams. So if 1 atom of calcium has the mass of 40.078 atomic mass units, we can't measure atomic mass units in the lab unless you had a really big machine that gives you precise numbers of atomic mass units. We have scales, we have balances, we can measure grams. Well, luckily, it's exactly the same number of grams. So really, you don't need to concern yourself with Avogadro's number at all. What you really need to concern yourselves with is understanding the relationship between atomic mass units and grams per mole. They're exactly the same thing. And then knowing that moles, the ratio of moles, is what determines how molecules and atoms bond with each other. They bond together in ratios of moles. And so if we know how many moles there are, we can automatically and easily calculate how many grams they have. So to obtain the mass of 1 mole of a substance, as we've seen, you just take all of the individual atoms, figure out how many grams they have in a mole, add them all together, and bingo, you've got the molar mass of the molecule. So like we've seen with ethanol, if it's C2H6O, we know we have 2 moles of carbon, we have 6 moles of hydrogen, and we have 1 mole of oxygen. So we just go, carbon is 2.11 grams, hydrogen is 1.008 grams per mole, and oxygen is 15.999 grams per mole. Now we would multiply this one by 2, we would multiply this one by 6, and we leave that one alone. And then we just sum them, and that would give us the molar mass of ethanol. Okay, we'll do a lot of examples of this, so don't worry. For instance, sodium chloride, the table salt in your house. If you look at the molar mass of sodium, now remember, it's the sodium ion and chloride ion, but the difference in mass between a sodium atom and a sodium ion is negligible because it's only the difference of 1 electron, and the mass of an electron is 1/2000th of an AMU, so it really doesn't affect the mass at all. So the molar mass of sodium atom is 23 grams per mole. The mass of a chlorine atom is 35.45 grams per mole. I would use the most number of significant digits you can find. I think the number of significant digits on this particular um, uh, periodic table is usually 5. It's 4 for the smaller atoms, but they always give 3 digits past the decimal. So use as many as you can, because again, you want to preserve that precision. So if you have a chance to use 5 significant digits, do it. Okay. So since there's 1 mole of sodium in a mole of sodium chloride, and there's 1 mole of chlorine, we just add those two together. So 23 plus 35, and that's the sum. So a mole of sodium chloride weighs 58.5 grams approximately. So you are going to get so used to this, switching back and forth, because sometimes we're going to need to know, if we're given, for instance, the number of grams of reactant. So if I have reactant X becomes product Y. If we're given moles, then it's a really easy thing to calculate. Oh, I have 1 mole of X, I'm going to make 1 mole of Y. Done. But what about if you're given, you have 23.56 grams of X, how many grams of Y are you going to get? Well, then you're going to need to figure out what the mole-to-mole ratio is. Here it's 1:1. So you're going to need to figure out how many moles of X is this. So you need to figure out what the molar mass of X is. That's the number of moles of X you're going to have. And you're going to get exactly the same number of moles of Y, but you're going to get a different mass, because we don't know what the mass of Y is. If we determine what the mass of Y is, then we can determine the mass of product. So we're just going to be using conversion factors like we've been using since the start of the class. So remember, we're either going to use this or this. So always when you're doing a conversion, the numerator must equal the denominator, because what we're actually doing is just multiplying by 1, right? So 1 mole of sodium chloride equals 58.45 grams. They're the same thing. So we can have them above or below, depending on whether we want to convert grams to moles or we want to convert moles to grams. Each is exactly equal to the other. So we'll use one when we need to convert grams to moles, and we'll use the other when we need to convert moles to grams, okay? So we use the grams to moles converting factor. When we have moles, we're given moles, but we're asked for grams. So in that case, I have moles. I eliminate moles, I'm left with grams. In the other instance, I've given grams. So I have grams. I'm going to be multiplying by moles over grams. I cancel grams and I'm left with moles. Always put the quantity you want on the top. Remember, I've sort of been harping on this for a while to you. I'm sure you're sick of me saying it. Put the quantity you want on the top, and the quantity you want to change gets put on the bottom. So that way you cancel what you want to change and you're left with the quantity you want, okay? So if you're performing a whole lot of changes, then you can do them all at once, or you can break them into stages. So always write down whatever quantity you're given in a question. If it starts with, you are given 2 moles of carbon, and you want to figure out how many grams of ethanol. Put a 6 there. Just write down what the quantity you're given. Determine which conversion factors you're going to need. So the first thing you would need to do is figure out how many moles of ethanol you get per mole of carbon. And then you would eliminate moles of carbon and be left with moles of ethanol. Then you would need to figure out, okay, I want grams of ethanol. So then I put grams of ethanol on top, moles of ethanol on the bottom, 1 mole of ethanol, grams, 1 mole ethanol on the bottom. I cancel moles of ethanol. And what am I left with? I'm left with grams of ethanol. So then I take all my numbers in the numerators, multiply all them together. I take all the numbers in the denominators, I multiply all them together. And then I have my total in the numerator, total in the denominator, get my final answer. So multiply and divide. And you should cross out, once you've crossed out everything, the only unit left should be the unit you want. So, and then all the numbers, all the coefficients in the top and the bottom then get calculated at the end. We'll do a lot of examples. Here's one right here. So, what is the mass of 3.987 moles of sodium chloride? What's the first thing we do? We write that down. We write down the number. I have 3.987 moles sodium chloride. So I write that down because that is the information I've been given. Now, I'm asked for mass, so that means my answer has to be in grams, right? So what am I going to do as a conversion? Well, I want to get rid of moles of sodium chloride, so I'm going to put that on the bottom. So 1 mole sodium chloride. And what do I want? I want the mass of sodium chloride. Okay, so this means that my conversion factor has to have the same amounts on the top and the bottom. And so on the bottom, I have 1 mole of sodium chloride. And on the top, I have to have a mass. What mass? The mass of 1 mole of sodium chloride, of course. So what's the mass of 1 mole of sodium chloride? So I do my calculation. We've done it before. I just look up what the mass of sodium is. And the mass of sodium on my periodic table is this. What's the mass of chlorine? Mass of chlorine on my periodic table is this, 35.453. I add those together, and I get a total of 58.443 grams. Now, like I said, use as many significant digits as you can, because it will increase the precision of your answer. So now I'm left with moles of sodium chloride. I'm getting rid of that because I have it on the top and the bottom. What am I left with? I'm left with grams of sodium chloride. And so it's just 3.987 times 58.443, and I get 233.0122 grams. Now, you're shrieking at the screen right now. That's too many significant digits. And you're absolutely right. That is too many significant digits. But how many do we need? I got 4 here, so I want 4 in my answer as well. So here is 4. So my final answer is 233.0 grams of sodium chloride. And I would want that in your answer as well. If you're given that as a test, on a test, what's the mass? You wouldn't just put 233.0. That's not correct. You want 233.0 grams. And really, you would want 233.0 grams sodium chloride, just to really make the point, okay? So this one, I'm going to do tomorrow before our workshop. So if you want to have a look at this, figure this one out. This is a molecule called potassium permanganate, and it's really good at oxidizing things. So not something you want to, definitely not something you want to drink. So figure out this one, and we'll do it together tomorrow. So now we're just basically going to look at how do we use this mole to mole, mole to gram ratios. So basically we need it to balance reactions because we have to have the same number of atoms. If we're looking, let's say that this is our reaction. We have to have the same number of atoms on each side. So we have 4 atoms of hydrogen. There's 2 molecules of hydrogen, and each molecule has 2 atoms, so there's 4 atoms of hydrogen. There is 2 atoms of oxygen. 1 molecule of oxygen, 2 atoms of oxygen. So on the other side, on my product side, I got to have exactly the same number of atoms. That's because mass is conserved in chemical reactions, and if mass is conserved, moles are conserved. So I have to have the same number of atoms and the same mass on both sides. So when it's converted into water, you can see the ratios are now the same. They're in a different form. The molecules are now bonded, hydrogen is now bonded to oxygen rather than hydrogen to hydrogen and oxygen to oxygen. But the ratios are exactly the same. I still have 4 atoms of hydrogen, and I have 2 atoms of oxygen. So this equation is now balanced, meaning I have the same number of atoms on both sides. And so if I have the same number of atoms on both sides, the mass on both sides is the same too, because the atoms don't change. The atoms don't change mass when they react. They don't change their mass. What do? They're just swapping electrons back and forth. The mass of electrons don't change either. And so we should have exactly the same mass on both sides. So they're balanced in terms of molar amounts of reactants and products. That's where the moles really come into effect, because we can see that we have 2 moles of hydrogen molecules versus 1 mole of oxygen molecules. So for every 2 moles of hydrogen molecules, we get 2 moles of water. So it's a 1-to-1 relationship. For every 1 mole of oxygen, we get 2 moles of water. 1 mole of oxygen, 2 moles of water. So we can always figure out if we're given either the mass or the number of moles of our reactants, we can always figure out how much product we're going to get. And the opposite. If we're given the amount of product, we can always figure out what the mass and the number of moles of reactants are. And this is the very painful subject called stoichiometry. And oh boy, you're going to hate stoichiometry. How much? This much, I'm afraid. Yeah, we're going to be doing like stoichiometry chemistry is basically stoichiometry. It's ratios. Ratios of atoms, ratios of moles, ratios of mass. And yeah, frustrating chemistry students in 1792. It's been a long time. In fact, it was stoichiometry that allowed the original, like old-timey chemists to figure out what masses of elements were. So they would react an element that they knew the mass of with an element that they didn't know the mass of, and then determine the mass of the product. by figuring out what the mass of the product and the ratios of the two elements, they could then figure out what the mass of the other element was. So, been doing this for a long time. So this is an analogy that's used a lot. Making cheese sandwiches. You're making a grilled cheese sandwich. To make a grilled cheese sandwich, you need 2 pieces of bread and one, I use more than 1 piece of cheese myself, but yeah, 1 piece of cheese. That gives you a cheese sandwich. But if you had 10 loaves of, or 10 slices of bread and 10 slices of cheese, how many sandwiches could you make? Well, you'd have to figure out, first, if I converted all my bread to sandwiches, that would be 2 slices, that would be 5. So that would give me 5 cheese sandwiches. Well, how many cheese sandwiches could I make with 10 slices of cheese? Well, there's only 1 slice of cheese per sandwich, and I got 10 slices, so I could make 10 sandwiches. But if one of my reactants will only give me 5 products, and the other one will give me 10, how many am I actually going to make? I'm only going to be able to make 5, because I'm going to run out of bread before I run out of cheese. And so we call that the limiting ingredient, or the limiting reactant. Bread is limiting. It limits the amount of product you can make. And the excess is cheese. I'm going to have cheese left over. And that happens all the time in chemical reactions. You're not always going to have exactly the right amount of reactant A and reactant B to make a product, and they each get consumed completely and there's nothing left over. That rarely happens. Usually you're going to have one is going to be in excess, and so the other one will be consumed, the limiting one will be consumed completely, and the excess reactant will be left over. And in this analogy, we would make 5 products. This would be gone completely because we would have used them all up, and we would have 5 pieces of cheese left over as our excess reactant. So a balanced chemical equation uses symbols to represent both the identities and the relative amounts of substances undergoing. This is the burning or the combustion of methane. So here I've got methane, and when I combust something, the combustion reaction just means I'm burning it in the presence of oxygen. That's all combustion means. I'm burning it in the presence of oxygen. And when you burn a hydrocarbon, this is a hydrocarbon. Why do we call CH4 a hydrocarbon? Well, it's only got hydrogen and carbon, hydrocarbon. And when you burn a hydrocarbon, you get 2 products. You get carbon dioxide and you get water. So now we need to balance that equation. So I have CH4 and I've got oxygen. So I'm going to make 2 products, CO2 and water. And already you can see that that gives me too many atoms of oxygen on one side. If I had just O2 over here, that would give me 2 atoms of oxygen. But on the other side, I would have CO2 and H2O. That's 3 atoms of oxygen. That's not balanced. So what do? I add another mole of water to give me an even number of oxygen atoms. Now I have an even number. Now I've got 4. So I go back. I need 4 oxygens now on the reactant side. So I put a 2 there. Now everything's balanced. I have 1 carbon on each side. There's my carbon here and my carbon there. I have 2 atoms of oxygen in my waters, and I have 2 atoms of oxygen in my carbon dioxide for a total of 4. And I've got a total of 4 over there. Okay? So this is how we write a chemical reaction. This arrow tells us the direction that the reaction's going. And the reactants are always going to be on the left side. So here's my reactants on the left side. Here's my products on the right side. So this is an oxidation reaction. It is a metal, magnesium, reacting with oxygen. And we know that oxygen really likes electrons. And so it's going to be taking the electrons from magnesium. And when it takes the electrons from magnesium, magnesium goes from being uncharged to having a +2. And oxygen goes from being uncharged to -2. So oxygen steals those electrons. And so since oxygen is in a molecule with 2 atoms, we're going to need to balance this equation. I have 2 atoms of oxygen here. I have only 1 atom of oxygen in my product. So I need another mole of product. I need to put a 2 here to make up for the oxygen deficiency on the product side. I need 2 of them. The minute I do that, now I have too many magnesium atoms on the right side. I only had 1 on the reactant side. So I put a 2 there. Now everything is balanced. And it gives you the ratio for every 1 mole of oxygen molecules. I need 2 moles of magnesium atoms and molecules. And they make 2 moles of my product, which is magnesium oxide. That is a very strange looking M. So here's an example we'll do. So we go back to the old tried and true, making water. So this is if you combust hydrogen in the presence of oxygen, you make water. And this is why hydrogen fuel cells are considered a non-polluting form of pushing cars around, because when you burn hydrogen in the presence of oxygen, the only emissions you get are water. And that's not harmful to anybody. So how many moles of oxygen react with hydrogen to produce this many moles of water? So we write down what we're given. What are we given? We are given 27.6 moles of water. And so we want to know how many moles of oxygen are present. So what is the ratio? We want, why does it 6 keep disappearing? So we want, our final answer, we want moles of oxygen. So it's so bizarre. Stay. So I want moles of oxygen, and there it goes again. And there's be something weird with my screen. So I want moles of oxygen, and I want to get rid of moles of water. So what is the ratio of oxygen to water? For that, I look at the balanced equation. And it says for 2 moles of water, there is 1. And when you're writing a balanced equation, you never include the 1. The 1 is assumed. If it doesn't have any number there, that number is assumed to be 1. So 2 moles of oxygen, or 2 moles of water for every 1 mole of oxygen. We get rid of our moles of water, and then it's just it's the disappearing 6. Then it's just 27.6 times 1 divided by 2, and that gives us, it's so bizarre, that gives us 13.8 moles of oxygen. Okay? Now again, this is one I'm going to be doing with the class tomorrow. So here we have ammonia and oxygen. And when you react ammonia with oxygen, you produce water and nitrogen gas. So this is not balanced. So balance this equation and then figure out how many moles of water are produced when we have this much ammonia. There must be this like one spot on my screen that does not like being written on. So always, this is a good point to figure out. Always assume that if you see a chemical reaction, it is not balanced. Okay? Always assume that it's not balanced and you need to balance it. Because I will do that on tests because I'm mean. I will just give you a chemical reaction and ask you, like for instance here, I have this much moles of ammonia. How many moles of water are going to be produced? And so you would look at that and say, well, I have 1, 1, 1, 1. All the coefficients are 1, so it must be 1.65 moles of water because they're the same. So you'd be assuming that's a balanced equation, and it isn't. So always, always, always assume that it's not balanced, and then balance it. A lot of the times it will be balanced, but you need to make sure that it is, okay? So, I can't erase that now. Nice. Oh. There we go. So you're going to be getting a lot of these problems. Mole to mole, mass to mass. So these are all stoichiometry calculations where you have mass, moles, you're going to be converting them back and forth. So if you're given moles of substance A, you then figure out what the moles of substance B are with the ratio of moles to moles from a balanced reaction. And then you just figure out what the molar mass of B is, and then you get grams of B. It's just a matter of figuring out what information are you given and what information are you asked for. So you need two pieces of information. You always need to have a balanced reaction. That is number one. You've got to have a balanced reaction. Without a balanced reaction, you're lost. You have to have a balanced reaction. The other, you need to have your periodic table with you because you need to figure out what the molar masses of everything involved in. So you get the mole ratios from the balanced equations, and then you get the molar masses from your trusty periodic table. So here's an example. Now, this says it's a balanced chemical reaction, but I might be lying. So let's double check. So this, what's the name of that? Anyone? Right, that is iron 3 oxide. So I have iron 3 oxide, and I'm reacting it with, right, sulfur trioxide. And what does that give us? It gives us iron 3 sulfate. Right, excellent. So let us check and see that it is balanced. So let's have a look. I have 2 moles of iron on one side, and I have 2 moles of iron on the other side. So iron, we're good. So then I double check and see how many moles of sulfur in each one. I have 3 moles of sulfur here. So I check my sulfur. I've got 3 sulfurs here. And I've got 3 moles of sulfate ion, and there's 1 sulfur in each sulfate, so 3. So Fe is good, sulfur is good. So I've got 2 irons, I got 3 sulfurs. How many oxygens? So now there's oxygen in both of the reactants. So we need to add them both, right? So I've got 3 here, and I've got 3 there, but I've also got 3 molecules. 3. So 3 plus 3 times 3, that's 12. So I've got 12 moles of oxygen. Then I look at the products. I've got 3 moles of sulfate ions, and there's 4 oxygens in each sulfate. 4 times 3 is 12. All right, so I got 12 oxygens on both sides. So that is a balanced reaction. Now I'm good to go. But remember, always, always check. Because there might be a typo, I just might be being evil, or I just may have given you an unbalanced equation and say this isn't unbalanced. Go ahead and balance it. So let's figure out what the answer is. So what are we given? Always write down what we're given. We're given 3.59 moles of iron 3 oxide. This is going to make me insane. And then we're asked how many grams of sulfur trioxide will react with that. So that means there's 2 things we need to figure out. First, we need to figure out how many moles of sulfur trioxide will react to it. And then second, we need to convert those moles to grams. Let's do the first one. Always do the first thing first. Always do the mole to mole relationship first. So we look at at our balanced equation, and we can see that there are 3 moles of sulfur trioxide for every 1 mole of iron 3 oxide. So I want to get rid of iron 3 oxide moles, and I want moles of sulfur trioxide. So there's 3 sulfur trioxides for every 1 iron 3 oxide. That gets rid of moles of iron and leaves me with moles of sulfur trioxide. That's what I want. Next, I want grams, right? Because that was the actual question. So we're going to put grams sulfur trioxide here and moles sulfur trioxide on the bottom. That eliminates moles of sulfur trioxide. Now, all I need to do is figure out what the molar mass of sulfur trioxide is. So, moles of sulfur trioxide, that is 1 sulfur and 3 oxygens. 1 mole of sulfur, I look it up in my periodic table, is 32.056 grams. A mole of oxygen is 15.999 grams. I multiply that by 3, add them together, and I get a total of 80.053 grams. And you can always double check this. You can always Google this, right? You can't do it on a test though. So get used to calculating it this way. And then you can always double check your answer, like on a worksheet or something, or in a lab or report or anything like that. You can always just look up the molar mass of these things. I mean, I do. But on a test, you're not going to be able to look things up in Google. You need to calculate them for yourself. So get used to doing that and then double check your answer. I actually haven't double checked my answer. I probably should. So 1 mole of sulfur trioxide is 80.053 grams. So now I multiply 3.59 times 3 times 80.053 divided by 1 divided by 1. So my final answer is, let me erase some of this stuff. My final answer is 862.1708 grams. Now, I'm not done because I always go back. This is the very last thing I do, is check and see how many significant digits there should be in the answer. There's 3 in the number of moles. That's the 3 in the amount of information you're given. So there should be 3 in the final answer. 1, 2, 3. My final answer is 862 grams. Not 862 decimal. That's not necessary because 8 and 6 and 2 are all non-zero, so I wouldn't have to. If the answer was 860, my final answer would be 860 decimal grams to indicate that this 0 is a significant digit, okay? Now this one, again, we'll be doing this one tomorrow. So double check that it is balanced, and then if you have that many moles of water being consumed, how many grams of sugar, glucose, are going to be created. Okay, we're going to do that one tomorrow. So a mass to mass calculation is if you're given the mass of one substance and you're asked for the mass of another one. So then you have to do 3 conversions. You need to take, if you're given the mass of one of the products or reactants in a reaction, you then need to convert that to moles, because, as I'm going to keep hammering the point over and over again, grams don't react with grams. Moles react with moles. So the number of grams of something does not help me in trying to figure out what happens in a chemical reaction. I need to know how many moles that is. So the very first thing I do is then figure out how many moles that is. So I convert grams to moles. Then I look at my balanced equation. Again, I have to have a balanced equation. If I don't have a balanced equation, I am hosed. So I figure out moles of substance B based on the balanced equation. If I have 5 moles of substance A, how many moles of substance B am I going to get? Well, if there's a 2-to-1 ratio of B to A, if there's twice as much B as there is A, that means I'm going to get 10 moles of substance B. Okay, I got 10 moles of substance B now. However, that wasn't the answer I'm looking for. I've been asked for the mass of substance B. So now I need to do another conversion. Then I need to convert moles of substance B back to grams. So this one takes the most work. If you're given the mass of something and asked for the mass of something else, you need to do 3 conversions. So let's do one here. So this is a reaction. We have methane, and it reacts with chlorine gas. So one thing to remember, most gases, if they're elemental gases, are going to be a molecule. The only ones that aren't are the noble gases. So if I say moles of oxygen gas, I mean O2. Moles of hydrogen gas, I mean H2. Moles of nitrogen gas, N2. Moles of chlorine gas, fluorine gas. They're all 2 atoms. in the molecule. They're all diatomic because they're not stable as atoms. They need to come together and share electrons in order to become more stable. So I've got methane, CH4. I have got chlorine gas. And what do I make? I make carbon tetrachloride, which is something that used to be used for dry cleaning until we figured out it caused cancer, and then we don't use it anymore. And HCl, or hydrochloric acid, or you could just call it hydrogen chloride. So the question is, how many grams of this product do we make if we start with 100 grams of that reactant? So we would start, as we do any of these problems, by just writing down what information do we have. Actually, the first thing we should do is check if it's a balanced equation. So let's check. So I've got 1 mole of carbon on each side. 1 there, 1 there. So that's groovy. I've got 4 moles of hydrogen atoms. 4 moles of hydrogen atoms, so that's cool. I've got 8 moles of chlorine atoms, 4 moles of chlorine gas molecules, but 8 moles of chlorine atoms. So 8 over here. And on the other side, I've got 4 chlorines there, and I've got 4 chlorines there. So 8. Yes, balanced. So all good. So what's the first thing? We write down the first thing, balanced equation. Second thing, look and see how many, what information are we given? We're given 100 grams of methane. It's doing it again. Okay. Now, but remember, I'm dealing with a reaction. Reactions don't happen in grams. They happen in moles. So I need to convert that to moles. I need moles of CH4. So how many moles, if I have 100 grams of CH4, how many moles is that? So I figure out I have 1 mole of carbon. That's 12.011 grams. I have 4 moles of hydrogen atoms. Those are 4 times 1.008 grams. So 12.11 times 4 times 1.008 grams. And that gives me a total of 16.043 grams, I think. Yeah. So 16.043 grams. That gives me the number of moles of CH4. So, next thing I need to do, I need to figure out what is the ratio of HCl to CH4. So, because now I need to know how many moles of HCl there are. So, I look at my balanced equation, and it says for every 4 moles of HCl, there's 1 mole of CH4 methane. So I want moles of HCl on top. So 4 moles HCl for every 1 mole of CH4. That cancels out moles of CH4. And we've also canceled out grams of CH4. Okay? Now I do my final conversion. My last conversion is I need to know how many grams of CH4. That is actually the answer I'm looking for. So I put grams, grams of HCl is what I'm being asked for. So I put grams of HCl on the top. On the bottom, I put moles of HCl. So for every 1 mole of HCl, how many grams is that? Well, I look up the mass of chlorine, and I look up the mass of hydrogen. I add them together, and it turns out that it is 36.461 grams. So now I check and make sure that all of my units have canceled. So I've got my grams of CH4 have canceled. My moles of CH4 have canceled. And now I'm canceling moles of HCl on top, moles of HCl on bottom. And the only unit I have left is grams of HCl. That is what I want. And so I multiply 100 by 1 times 4 times 36.461 divided by 16.04. And so my final answer is 909.08 grams of HCl. And then to finish, I check how many significant digits should I have. And I'm looking, and it says 100.0 grams of CH4 methane. That is 1, 2, 3, 4 significant digits. So my final answer would be 909.1. That would be my final answer. I would round up because of the 8 here. Okay? And then tomorrow we will do this one as a group. So to sum up, we use the mole to represent a lot of just a unit number of things. It is the number of atoms, the number of molecules, the number of ions. And it's just the number of atoms, molecules, or ions that it takes for the atomic mass to equal the molar mass. And it's a big, big, big number. That's not very important. We need to know that that's the molar mass comes from the atomic mass based on that many things. So we can always use the coefficients of a balanced chemical equation, and I make the point again, always check, to relate moles of one substance in a reaction to the moles of any of the other substances in a reaction. There could be 15 reactants and products, but if I have a balanced equation and just one amount of any of those, I can automatically figure out the amounts of all the other ones, just based on the ratios in the balanced chemical equation. And that is the hateful term stoichiometry. So if we're doing a mole to mass calculation, we take the number of moles, figure out the mass. But in a mass to mass calculation, we take the mass of substance 1, convert it to moles, figure out the mole relationship to substance 2. Once we have the moles of substance 2, turn that back to mass. So we need to do 3 conversions for that one. All right, so we're going to be doing a lot more of these. Next week's worksheet will pretty much be all of this. Balancing equations, figuring out the amounts of products and reactants. And then we're going to be figuring out excess reactants and limiting reactants, because that's also very, very important. All right, I will see you tomorrow night.